Greetings to you. We had discussed about the electronic structure of the atoms in the last class and previous class also. Where I had stopped is the interaction of electromagnetic radiation with matter, because spectroscopy is the measurement and interpretation of the electromagnetic radiation resulting in the absorption, emission, reflection, refraction, diffraction, etc. by atoms and molecules or other chemical species. So, all these processes are associated with changes in the energy states of the species or modification of its energy or intensity. So, what we are essentially saying here is the atoms, molecules and other chemical species will react with electromagnetic radiation, and the changes occurring in the atomic structure or the electronic structure could be related to changes in the electromagnetic radiation, because the change will be corresponding, that is 1:1. So, what is an electromagnetic radiation? So, what we want to say is an electromagnetic radiation is considered as a wave which carries energy from one location to another at a finite velocity. This velocity is 3 into 10 raised to 10. So, as the name suggests, the electromagnetic radiation has two components. One is an electric part, that is electric field, and another is a magnetic field. So, each of them are perpendicular to each other, and I think all of us are familiar with what is an electromagnetic radiation. I do not know how many of you are aware, but every day we are exposed to electromagnetic radiation, and any time of the day we are exposed to electromagnetic radiation. We see electromagnetic radiation all around us. Okay. So, what is an electromagnetic radiation? It is nothing but some sort of a light which we see. For example, the rainbow colors what you see in the sky, they are all electromagnetic radiations. The ultraviolet rays what you get from the sun in the morning, they are electromagnetic radiations. And then visible light through which you and I see each other, they are also electromagnetic radiations. And then you must have heard of several other types of electromagnetic radiations, which include infrared, radio waves, microwaves, cosmic waves, cosmic rays. All these are, as a group, they constitute electromagnetic radiation. So, each electromagnetic radiation, some of them we see them, some of them we do not see them, because our eye is not sensitive enough to capture the radiation. So, how do we define what is electromagnetic radiation? Look at this slide. Here I have written I have shown you an electromagnetic radiation, this slide. Here you can see on the top I have written the electromagnetic spectrum chart by the University of Colorado, Boulder, and that consists of gamma rays, X rays, ultraviolet rays, and then visible light somewhere in the middle, and near infrared, far infrared, microwaves and radio waves. Okay. Now, here you see I have listed the frequencies on the left side. For example, gamma rays have got the wavelength of 10 raised to minus 6 nanometers. They range from up to 10 raised to minus 2 nanometer. So, 10 raised to minus 2 nanometer is 1 angstrom unit. So, the effect of gamma rays end up, maximum wavelength of a gamma ray is 1 angstrom unit. And then we have X-rays, that is 10 raised to minus 1 to 10 nanometers. So, this is approximately about 100 nanometer total, because 10 raised to minus 2 to 10 raised to minus 1 and 1 nanometer, approximately 100 nanometers range, and the radiation which have a wavelength of this range are called as X-rays. You may not be able to see them, but you will be able to see the effect of X-rays on photographic plates when you go to a doctor to take the X-ray. Now, X-rays here you can see that the X-rays have got longer wavelength than gamma rays. Gamma ray is 10 raised to minus 2, whereas X-rays extend up to 10 nanometers. Now, as you go down, I have written here ultraviolet rays, which range from 10 to 100 nanometers. And then we also have, among the ultraviolet also, we have the far ultraviolet and near ultraviolet, that is vacuum ultraviolet it is called. I have not shown it here, but vacuum ultraviolet rays are up to 10 or 20 nanometers, followed by ultraviolet, and then after the ultraviolet range we have visible light. Now, the visible light, the range is from almost up around 1 micrometer, 1 to 1000 micrometer, up to 10 raised to minus 3 micrometers, and the visible light I have shown on the right side, expanding cone into violet, indigo, blue, green, yellow, orange and red. So, visible light, what we see around you, what you see, what I see, what all of us see, comprise of these 7 colors, violet, indigo, etc., but they range from around 1 micrometer range. Then we have, if you come back to this middle strip, after the visible light there is near infrared light, that is up to 10 micrometers, and after that I have far infrared, that is up to 100 micrometers, that also extends further down the line up to 1 millimeter. So, all these radiations, electromagnetic radiation corresponding to this range 10 micrometers to 1 millimeter or 1000 micrometer are known as far infrared. Then there are ways, electromagnetic radiation having still larger wavelength, that is from 1 centimeter to 1 meter. So, these are called microwaves. You are familiar with the microwave cooking, etc. It is not very unusual, and down the line we have from 1 meter to 1 kilometer and up to 100 megameter also we have what is known as radio waves. And the microwaves and radio waves comprise of ultra high frequency, VHF, high frequency, medium frequency, low frequency, etc. And still down the line we have from 100 kilometer to 1000 kilometer, it is audio waves. That means the electromagnetic radiation except this part are not visible to us, but they are in existence and they all constitute the same species except by differing in wavelength and frequency. Some of them we see, some of them we do not see, and our visible eye is limited to only a small portion of the electromagnetic radiation. Any other radiations we are unable to feel, at least see it with our naked eye. Feeling, yes. For example, infrared heating we are all aware it can be done, microwave heating can be done, microwave towers you would have seen all around us, etc. Radio waves you have heard of, all these, the whole thing constitutes an electromagnetic spectrum. So, the properties of electromagnetic radiation, I define them like this, that is the name of the unit. Normally this is how the electromagnetic radiation is described, its wavelength. So, the nanometer symbol is Nm, unit for wavelength, and this type of electromagnetic radiation is used in UV, visible and near infrared radiation, infrared range. We can also write angstrom, symbol is like this, and then it is also a unit for wavelength, and it is useful. If I write angstrom, if I had to describe any X-ray, I would describe it as having 10 angstroms, 20 angstroms, like that. That is its wavelength. Similarly, in UV visible also we describe in terms of angstroms, but that is all in older work. For example, if you study literature, scientific literature around about 40-50 years before, people would have described the UV visible range in terms of angstrom units, 4000 angstroms, 6000 angstroms, like that. But for convenience nowadays we do it in nanometers, and they are SI units also. So, next is millimicrons, units are again for wavelength, and that is in the visible range, but again it is in older work. We no more use these terms in our scientific literature. And then we do use microns and micrometers, and that is also unit for wavelength, but that is useful for infrared radiation only. So, such microns and micrometers are used in organic chemistry as well as in physics literature. Then we use a term what is known as wave number, that is centimeters inverse. Symbol is micrometer by wave velocity of light, that is c. Again it is used in infrared radiation. It is also used in UV visible radiation, but fairly less common. Then for describing high energy radiation, we use, instead of wavelength, we use electron volts. Okay. So, that is the unit for energy, and it is used for X-ray and gamma rays. Then we use hertz, that is the radio frequency, it is the frequency for symbol for frequency Hz, it is for length, and radio frequency and microwaves we describe them in terms of hertz. Then cycles per second, CPS, that is used in radio frequency, but that is also again less common in the current literature. Now, all these energies refer to, because all these energies refer to the wavelengths, there should be some sort of interconversion of energy and wavelength. For example, and if I write it in nanometer, 1 nanometer corresponds to 10 angstroms and 10 raised to 7 centimeters inverse. Its corresponding energy is 1.240 into 10 raised to 3, and its frequency would be 2.9979 into 10 raised to 11, and its energy in joules is 1.986 into 10 raised to minus 16. Similarly, if I choose any other column here, that is centimeters inverse, it can be described in terms of nanometers, in terms of angstroms, in terms of electron volts and energy and frequency. Same thing is true with respect to frequency, that also can be converted. There is some interconvertibility table, you need not by heart this, but it makes sense to know that all these forms of energies are interchangeable, interconnectivity is there. So, spectrometric region, this nanometers is the wavelength range used in UV visible spectrophotometry, angstroms in UV and X-ray, centimeters in infrared, electron volts for X-ray and megahertz for radio frequency. The corresponding analytical techniques are also you can easily identify here. For example, UV visible region is for colors, this is for X-ray is for bones etc., hard materials, infrared is for sun's radiation etc. All these things can be understood. Now, coming back to electromagnetic radiation, we say we call it electromagnetic radiation because it has two components. One is electrical field, another is magnetic field. That means, whenever an electromagnetic radiation is proceeding towards the in a particular direction, there is a component known as electric field and another component is known as magnetic field. Here I have tried to depict here the electric field like that in the x axis in red color. Now, the magnetic field is perpendicular to that and then it is in blue color. So, this is the wave nature of a single frequency of electromagnetic radiation. So, whenever we see an electromagnetic radiation going, I have to imagine that there is an electrical field like this and then there is a magnetic field perpendicular to that like this. So, if I am sitting here on a chair on a table, along the horizontal line there is one magnetic field and on the vertical space there is electrical field. Okay, so this is how we imagine and you can see the directions of the electric field and magnetic field here in this area. So, the magnetic field stretches upwards and electric field stretches upwards and magnetic field stretches horizontally. There is no hard and fast rule that it should stretch only electric field should stretch upwards, it is only relative as far as we are concerned. So, many properties of the electromagnetic radiation are conveniently described by considering it as a classical sinusoidal wave. This wave type of wave, once it starts from 0, it reaches maximum, again reaches 0, goes to -1 and again reaches 0 like this in terms of units. This is known as sinusoidal wave. And same thing is true even with the magnetic field that is shown in blue color here. That means, its value keeps on increasing until it reaches 1 and falls to 0 and then it reaches -1. More than that the values it will not be bigger. But for microwave this amplitude will be bigger and this distance wavelength is also bigger. But otherwise all the properties are essentially similar like this except in terms of quantity. So, we say that electromagnetic radiations are conveniently described by considering it as a classical sinusoidal wave with characteristic wavelength, because we know per a centimeter how many crests will appear, how many troughs will appear below the scale we call it trough, above the scale we call it how many crests and troughs. So, the what are the characteristics of an electromagnetic radiation is, its characteristic is wavelength, its characteristic is frequency, its characteristic is velocity and amplitude. if you describe any electromagnetic radiation with one single wavelength, you will be describing all other properties also simultaneously, because they are fixed for particular wavelength, and same thing is true with respect to all other parameters also. So, electromagnetic radiations pass through vacuum also, unlike sound waves. So, electromagnetic radiation does not need a medium. However, some properties of the electromagnetic radiations are also described as a number of streaming particles travelling in a wave form referred to as corpuscles or photons. Now, you can imagine a wave. If you imagine a wave in a pond, you can see that the pond surface is having troughs and crests, etc. Or if you throw a stone in a pond, it will generate waves which will have troughs and crests. But for that there is a medium required for example water. If the water is not there, you will not be able to see the troughs and crests, correct. So, if the medium is not there, then also the electromagnetic waves will be going through the same motions in the air. In this case, air acts as a medium, but we do not see the air, but the waves will be going through the same. Extending the analogy, suppose air is not there, then what happens? Will the electromagnetic radiations still need a medium, whether visible or not, to move from one point to another? Answer is yes, because in between we keep on receiving radiations from the sun on the earth, even though there is nothing in between. Okay, you can almost describe it almost as vacuum. So, if you take a radiation, create a vacuum in between, put a detector on the other side, you will still see the radiation on the other side. This is known as vacuum transmission. So, electromagnetic waves have got wavelength, frequency, they need a medium, and they need not need a medium also. Now, I can imagine that going back to this figure, you can also imagine, I can imagine a light particle, a particle made of a single light moving up like this, but it keeps on moving in this direction, right. So, when this, if I assume that this is a particle, when it reaches here, what happens to another particle will replace this from the source. So, I can imagine that every electromagnetic radiation is a stream of particles which keep on travelling through the same mechanism, having same amplitude, etc., in the same medium. That means, a number of light points are imagining, you can imagine a number of light points being thrown from the source towards a particular direction. Okay. So, the imagination can also we can extend the imagination to the electromagnetic radiation, that they are not only waves of energy, but they could be particles of energy carrying certain amount of energy, a fixed amount of energy along with them. So, this is known as corpuscular theory. So, some properties of the electromagnetic radiations we can easily define them or describe using particle theory or using a wave theory. Both of them are possible. The particle theory is explained by using by imagining that this source is emanating a number of particles throwing out, and these particles are known as photons. So, both of them are possible, and a characteristic wave, a typical wave can behave both as particle as well as a wave. In some cases it makes more sense to measure it as a wave, and in some cases it makes sense to use them as particles, corpuscular particles. Then can we use both? The answer is no. Why? Because according to Heisenberg's principle, it is impossible to measure the wave and particle properties of a photon simultaneously and exactly. It has got lot of quantum mechanical connotations, but essentially stated it means that you cannot pinpoint the position of a wave corresponding to its position as well as energy. So, wave and particle properties of a photon simultaneously, it is not possible. There is always certain amount of error associated when you want to measure the wave size as well as particle size at the same time. Therefore, it is convenient to imagine photons as having specific amount of energy radiating from a source and characterized by an electromagnetic wave. Okay. Now, the wavelength of radiation lambda can be visualized as the distance between two maxima of either electrical or magnetic components. This one, this is one maxima, this is another maxima. This distance measured either in angstrom units or centimeters or millimicrons or whatever it is, the difference between the two crests or two troughs. Okay. For example, I can do it from here to here, from this crest to this crest. So, both of them should be same. So, it is possible to measure this, and it can be visualized as the distance between two maxima of either electrical component or magnetic component. Both of them should be same for a given electromagnetic radiation. Now, the frequency mu is the number of waves in an electromagnetic radiation passing through any fixed point per unit time. So, that means you fix a particular place and how many waves pass through that point per second or per minute or something like that. So, when a photon passes a particular region of space, the electric and magnetic fields oscillate with the frequency. You can show this thing by a simple experiment, and therefore, only frequency is truly characteristic of a particular radiation. That is what we say. If you calculate the frequency, electromagnetic radiation is fixed. Okay. Now, mathematically, how do we write an electromagnetic radiation? We write it as a sine wave. I have already explained to you that the amplitude for a sine curve, it reaches a maximum and then a minimum, and then all the values are in between. So, we write A is equal to A0 into sine theta. That means, when theta is 0, sine theta is sine theta is 0. So, the value of amplitude will be 0. So, as the theta increases, sine theta also increases, reaches a maximum of 1, and then in that case A would be equal to A0, that is the maximum, and then again it will decrease as you proceed along this thing. So, A0 is the peak amplitude and theta is a continuous variable by which the photon moves forward. Now, alternately we can also write A is equal to A0 into sin omega t, and this omega t is equal to theta, and W omega is the angular velocity in radians per unit time. You can imagine that the radiation is going through a 360 degrees, first 0 to 180. If you imagine a range from 0 to 360 degrees, from 0 to 90 it reaches maximum, 180 it reaches 0, 270 it reaches -1, and 360 again it reaches 0. So, this cycle keeps on occurring again and again. So, it will be describing a sinusoidal wave, as we have said earlier. And then a complete cycle occurs when omega t changes from 0 to 360 degrees, and this is called one oscillation or one period. That is, the path described by an electromagnetic radiation from 0 to 360 degrees is one oscillation. Hence, the time over which one complete oscillation occurs is given by omega divided by 2 pi, that is number of cycles, or that is known as frequency. 1 over t is the frequency we call it, and then that is described by 2 pi by omega. It is only a simple mathematical representation of the radiation. And then for any any wave moving at a constant velocity v, we can write the velocity is the number of cycles per second followed by wavelength multiplied by wavelength. V is the frequency in meters per second and V is in hertz, so that is cycles per second, and lambda is in meters. So, the frequency is proportional to the energy, and that is again given by E is equal to h mu. Mu is the frequency. So, the energy of any electromagnetic radiation, h is a constant, that is known as Planck's constant. So, the energy of a given system corresponds to a fixed frequency or fixed part of the electromagnetic radiation. So, in this equation h is Planck's constant, that is determined experimentally as 6.62 into 10 raised to 7 ergs when E is expressed in ergs, and that is also equal to 6.63 into 10 raised to minus 34 joules, that is when E is expressed as joules. Sometimes it is convenient to use wave number denoted by sometimes it is denoted by 1 over frequency, that is wave number. It may be noted that regardless of the units of expression of any electromagnetic radiation of frequency, frequency will have unique wavelength and unique energy and unique frequency. Every frequency will have unique wavelength and unique, this is what we have been saying since long time. And the longer the wavelength, the lower is the energy and frequency. So, frequency is closely related to the temperature of any object. It can be expressed as a Boltzmann constant expression. E is proportional to Kb into T, where Kb is Boltzmann constant described by 1.380 into 10 raised to minus 6 ergs per degree, that is Kelvin per atom. If we consider the energy per mole of the material, you can also write that E is proportional to RT, that is R is gas constant and T is the temperature in absolute scale.